In this lecture, we will talk about solar cells. Here are the topics that we covered in the previous lecture. In today's lecture, I will give an introduction to solar cells. Then I will talk about a comparison of solar cells and photodetectors. We will discuss some basic diode concepts because the fundamental building block in a solar cell is a p-n junction diode, and it's basically a fundamental building block in LEDs and photodetectors as well. So we are going to revisit some of the diode concepts. Then I will talk about photo generation. We will discuss solar cells IV characteristics, tunnel junctions for more complicated and advanced solar cells, and finally we will discuss some non-idealities in solar cells. Solar cells and photodetectors are semiconductor devices that convert an optical input into voltage and current. It means they convert light into electrical signals, into voltage and current. The input is light and the output is voltage and current. There are a few differences in solar cells and photodetectors. We will talk about the differences in a bit, but assume a solar cell. And as I already discussed, that the basic building block in a solar cell is a p-n junction. So when light is incident on this p-n junction, and assuming that the energy of the incoming photons is greater than the band gap of the semiconductor, this light would result in the generation of electron-hole pairs. But the condition is the energy of the incoming photons should be either greater than or equal to the band gap of the semiconductor. Like for example, if the solar cell is composed of silicon material, NNP-type layers of silicon, we know the band gap of silicon is 1.1 electron volt. So the energy of the incoming photons should be either equal to or greater than 1.1 electron volts in order to generate electron-hole pairs. Now these electron-hole pairs, the holes move towards the p-type layer and the electrons move towards the n-type layer. The separation of these charges result in a voltage, and the flow of these charges through the external resistance results in a current. And the product of voltage and current is actually power. So basically a solar cell is used to power our devices. On the other hand, the construction of a photodetector is similar to that of a solar cell with slight differences. Solar cell is a wide area device. Our goal in a solar cell is to create as many electron-hole pairs as possible so that we can achieve a maximum voltage and a maximum current out of this device, resulting in high power. So the goal in a solar cell is to achieve high electrical power, while the goal of a photodetector is to sense light or to detect light for different applications. For example, for communication purposes, or for fire alarm, or for other medical applications, quality analysis of different kind of oils and that kind of stuff. So the goal of a photodetector is to sense or detect light. We don't need to bias a solar cell, but in case of photodetector, some configurations do require biasing. For example, p-n photodetectors or p-i-n photodetectors need to be biased, reverse biased, so that we can increase their depletion width, resulting in lower capacitance. And if the capacitance is lower, the response time or the speed of the photodetector would be higher. And which is the goal of photodetector? We would like to detect as fast as possible for different applications, especially for communications. So photodetectors are intended to work as sensors or receivers. That's why they are optimized for sensitivity and speed. While solar cells are meant as power sources, the goal in case of solar cells is to convert light into electrical power. We don't really care about speed in case of solar cells. Here I have listed solar cells versus photodetectors or photodiodes. In case of solar cells, we have larger areas, and the goal of this larger area is for the light to be incident on a maximum surface area, resulting in large number of electron hole pairs, and these electron hole pairs then result in voltage and current across the device, giving us electrical power. While in case of a photodiode, we don't really care about large electrical power. Even small electrical power is sufficient. So photodetectors and photodiodes are small area devices. If they are small area devices, we know capacitance is inversely proportional to area, so their capacitance would be smaller. The RC time constant would be smaller, resulting in a smaller delay for photodetectors. So we can have smaller sizes or smaller areas for photodetectors as well. Another point is that in solar cell, we don't really bias these solar cells. Well, in case of photodetectors, for some configurations, we might need to bias them, like the PN photodetectors and the PIN photodetectors. We reverse bias them so that we can extend the depletion width, decreasing the capacitance, resulting in a smaller response time, achieving higher speed. In solar cells, we don't really care about the response time, but in photodetectors, we do care about the response time. We would like to have smaller response time or higher speed for photodetectors. The applications of solar cells are calculators, communication satellites, battery chargers, and a lot of other applications, while the applications of photodetectors are intruder alarms, smoke detectors, remote controls, home door sensors, fire alarms, and a lot of other applications like that. Well, let me close the door because I see some interference. Here is our solar radiation spectrum. So basically, the solar radiation has wavelengths in the range of 200 nanometers to approximately 3000 nanometers, or 0.2 micrometers to 3 micrometers. But we have high intensity of the solar spectrum in the visible light range. As you can see, the intensity in the visible light range is higher. Like the range of visible light is from approximately 400 nanometers to 750 nanometers, and then the peak intensity is around 550 nanometers, which is the green light range. So we have most of the intensity of the solar light or power per unit area of the solar radiation in the visible light range. Also, we see that the solar spectrum actually kind of replicates black body radiation at 5250 degrees C, which is the black curve over here. Now, black body radiation means, assume, for example, tungsten. If you heat tungsten up to 5250 degrees C, it's going to result in radiation in this spectrum range, in this wavelength range, from 200 nanometers to approximately 3000 nanometers. Then the yellow portion over here actually is sunlight at the top of the atmosphere. So as you can see that the yellow portion over here kind of replicates black body radiation in the range at 5250 degrees C. Then the red region represents solar spectrum at sea level. Now you see that solar spectrum, the intensity of solar spectrum at sea level is lower as compared to sunlight at the top of the atmosphere. Why is that so? Because light has to pass through our atmosphere, and in this process, since we have oxygen and water vapors and a lot of other gases in the atmosphere as well, so in this process some of the light would be absorbed and some of the light has to go through scattering phenomenon. So because of those phenomenons, the solar spectrum actually loses some of its intensity when it passes from the top of the atmosphere and it arrives at the sea level. So that's why you see that the intensity at sea level is lower as compared to the intensity of sunlight at the top of the atmosphere. Then we have the same spectrums. The blue curve over here represents black body radiation as at 6000 Kelvin, and the red curve over here represents solar spectrum at the top of the atmosphere. There is another terminology, it's called air mass, and air mass represents the angle of incidence of the solar spectrum on Earth. Like for example, at the top of the atmosphere, it's represented with the red curve. We call it air mass 0. Then you see this green curve over here. Excuse me. Excuse me. This green curve over here, it's air mass 1.5. So it's basically light passing through the atmosphere at a certain angle. Moving on to the next slide, for example, we can describe it better. So assume that this yellow portion over here is the atmosphere. Now at the top of the atmosphere we have the solar spectrum, and it's going to have maximum intensity, and it's represented with air mass 0. And now another situation is this solar spectrum passes through the atmosphere vertically. Now assume that this is our Earth. So it directly passes through the atmosphere, making a 0 angle with the vertical axis. So this is called a solar zenith angle of 0 degrees. So this solar spectrum passes through the atmosphere at 0 degrees solar zenith angle. And the air mass is calculated using a simple formula. Air mass secant of theta, the angle over here is 0. So air mass secant of 0 is air mass 1. So this actually represents air mass 1 when light passes through the atmosphere at 0 degrees solar zenith angle. Consider another example. Now this would be around noon time when sun is like directly above our head. But there could be another example, for example, in the afternoon. Now this solar spectrum is making an angle to the Earth's surface. So now this solar spectrum, this solar radiation has to pass through the atmosphere at an angle. So it passes through a larger volume of gases. It means that the intensity at this angle would be lower as compared to the intensity at 0 zenith angle. Now for this case, depending on the angle, we can calculate the air mass. If the angle is 0, we call it air mass 1, and the intensity is 0.925 kilowatt per meter square. When the angle is 60 degrees, secant of 60 is 2, so we call it air mass 2, and there the intensity reduces at this angle to 0.691. If the angle is 45 degrees, air mass becomes air mass 1.4. Generally, we test our solar cells at standard test conditions. It should be tested at room temperature. That is one of the standard test conditions. We have a solar simulator at our Center for Advanced Electronics and Photovoltaic Engineering. And for the solar simulator, I told you one of the standard test conditions is 25 degrees room temperature. Another test conditions is that the intensity should be 1 kilowatt per meter square or 100 milliwatts per centimeter square. The third test condition is it should be tested at AM 1.5. AM 1.5 means a solar zenith angle of 48.2 degrees. So these are different terminologies of the air mass. So air mass basically accounts for the solar radiation passing through the atmosphere, resulting in a decrease of the intensity of the solar radiation as it passes through the atmosphere at different angles. Here is a simple formula for calculating the energy of a photon. E is equal to hc divided by lambda, where h is the Planck's constant, c is the speed of light, is equal to 1.24 divided by lambda in micrometers, or in nanometers you can say 1240 divided by lambda in nanometers. Excuse me. So, for example, if the wavelength of light is 400 nanometers, just enter its value and it's going to give you the corresponding energy of the photon. Or you can also calculate the wavelength corresponding to a particular band gap of semiconductor. For example, for germanium, the band gap is 0.67. So the corresponding wavelength becomes 1.85 micrometers or 1850 nanometers. For silicon, the wavelength is 1100 nanometers. Gallium arsenide 873 nanometers. Gallium nitride 365 nanometers. This formula also gives us the upper cutoff wavelength for photodetectors and for solar cells. For example, for silicon, the upper cutoff wavelength is 1107 nanometers. Any wavelength above 1107 nanometers would not result in the generation of electron-hole pairs in silicon-based solar cells. Similarly, for gallium nitride, any wavelength above 365 nanometers would not result in the generation of electron-hole pairs. So, the upper cutoff wavelength for these solar cells and photodetectors based on these semiconductor materials is determined from this simple formula. How about the lower cutoff wavelength? There is also a lower cutoff wavelength for solar cells and photodetectors. The lower cutoff wavelength can be determined using absorption coefficient. Now here is absorption coefficient on the vertical axis plotted versus wavelength for different semiconductors, for silicon, for germanium, for indium gallium arsenide, for gallium arsenide, the green curve for indium phosphide, and for so many other materials. Another parameter is absorption depth or penetration depth. Now, when light is incident on a solar cell, it's going to travel inside the material up to a certain depth, and that depth is called absorption depth. Absorption depth is inversely proportional to the absorption coefficient. Like, for example, assume a short wavelength of 400 nanometers or 0.4 micrometers. At 0.4 micrometers, the absorption coefficient is 1 into 10 to the power of 6 per meter. So the penetration depth would be 1 over absorption coefficient, or 1 over 10 to the power of 6, or 10 to the power of 6 minus 6 meters, which means the absorption depth is 1 micrometer. So at smaller wavelengths, the absorption coefficient would be higher, but the light would travel shallower into the semiconductor device. Like at 400 nanometers, this light can travel only up to 1 micrometer inside the device. But at longer wavelengths, it can travel deeper into the semiconductor material. For example, at 900 nanometers, it can travel, the absorption coefficient is 10 to the power 5, the absorption depth would be the inverse of it, or it can travel down to 10 micrometers inside the semiconductor device. Now, what is the problem when it at lower wavelengths? The problem at lower wavelengths when we have higher absorption coefficients is that this light would be absorbed close to the surface of the semiconductor material at smaller depth inside the semiconductor. When it is absorbed close to the surface, electron hole pairs would be generated, but we know that we have a lot of defects close to the surface of semiconductors. We have a lot of dangling bonds close to the surface of the semiconductor. So because of these defects and dangling bonds, the generated electron hole pairs would be recombined. So these photons which have shorter wavelengths do not really contribute to voltage and current, because the generated electrons, they are annihilated once again, they are of no use. So absorption coefficient sets a lower wavelength, a lower limit on the wavelength of light. For example, for silicon based photodetectors, we can say that the lower cutoff wavelength is approximately 400 nanometers. So the upper cutoff wavelength is dictated by the band gap of semiconductor. For silicon, 1100 nanometers, and the lower cutoff wavelength is dictated by the absorption coefficient, approximately 400 nanometers for silicon. In the photovoltaic effect, we already discussed that the input is light. If the energy of this incoming light is greater than the band gap of semiconductor, it will result in the generation of electron hole pairs. Electrons move towards the n-type layer and holes move towards the p-type layer. Separation of these result in voltage, and the movement of these carriers result in a current. Once again, the concept of photovoltaic effect is described with the help of this block diagram. Absorption of light results in the creation of electron hole pairs, separation results in voltage, and their movement results in current, and the product of the two results in electrical power. So here is an example of light with three different energies. We have this light where the energy of this light is smaller than the band gap of a semiconductor. Similarly, we have another photon where the energy of the photon is comparable to the band gap of the semiconductor. And we have a third photon where the energy of this photon is much greater as compared to the band gap of this semiconductor. So for this photon, where the energy of this photon is smaller than the band gap of a semiconductor, it's not going to result in the generation of electron hole pair. It's going to transmit through the semiconductor. It's just going to flow through the semiconductor, transmit through a semiconductor without disturbing its electronic behavior. For the second photon, where the energy of this photon is comparable to that of the band gap of semiconductor, it will result in the generation of electron hole pair. Electron transitions from the valence band to the conduction band. In the third case, we have another photon where its energy is much greater than the band gap of semiconductor. Once again, it's going to result in the generation of electron hole pair. But because of high energy of the photon, this electron will transition much higher to the conduction band. And we know that electrons tend to settle down at the minimum level of conduction band, at the bottom of the conduction band. So with the passage of time, this electron would start moving towards the bottom of the conduction band in steps, called because of Auger recombination. But in this process, when it transitions to the bottom of the conduction band, it's going to lose some of its energy in the form of lattice vibrations or phonons, resulting in heating of the device. Let's talk about solar cell operation, and for that purpose let's move forward to the structure diagram of a solar cell. Here is a simple structure of a solar cell in which we have an N plus layer on the left side. We have a p-type layer on the right side. This p-type layer is connected to a contact on the right. We call it the back electrode. And the N plus layer is connected to another electrode on the left. We call it finger electrode. And this concept of finger electrode and back electrode would be illustrated more in the upcoming slides. We also know that whenever we have a p-n junction under thermal equilibrium, we also have a depletion width associated with the p-n junction. So in this case, we are going to have a depletion width at the metallurgical junction and we also know that the depletion width is inversely proportional to the doping concentration. So on this side we have a heavily doped material. It means that the depletion width would be smaller on the inside. And on this side we have a lightly doped material, so most of the depletion width would be accommodated inside the p-type layer. Now assume three different photons. A photon with a shorter wavelength, violet light for example. Violet light have wavelengths in the range of 400 to 450 nanometers. Then assume another photon which has medium wavelength, for example green light, where the wavelength range is 520-ish to approximately 580 nanometers. And assume a longer wavelength light, red light, where the wavelength range of red light is from 620 to 750 nanometers. So if we know from the previous slides that shorter wavelength light has high absorption coefficient, which means that shorter wavelength light can travel shallower into the semiconductor material. So the shorter wavelength light would be absorbed close to the surface of this device. Now this results in the generation of an electron-hole pair. The electron would be collected by this electrode, and the hole would move towards the p-type layer so that it can be collected by the back electrode. But there is condition. These carriers which are generated, they have a certain carrier lifetime. For example, in silicon, electrons and holes have approximately a carrier lifetime of approximately 1 microsecond. And these carriers, they can travel only during lifetime. They can travel a particular distance in their lifetime. And that distance is called the diffusion length. The diffusion length can also be represented with this formula, where the diffusion length is equal to square root of the diffusion coefficient times the recombination lifetime. But as for now, you can just assume that carriers have a particular lifetime and they can travel a particular distance within their lifetime. And for hole, this distance is called the diffusion length. So if the depletion region is within the diffusion length of this hole, then this hole would be able to travel towards the depletion region. And since we don't have carriers inside the depletion region, it's not going to recombine inside the depletion region. It's going to travel towards the p-type layer, and it's going to be collected at this back electrode. But if this whole electron-hole pair is created away from the depletion region, then it's going to recombine. Now consider the medium wavelength. Now the medium wavelength light would travel up to a medium distance inside this depletion, inside this semiconductor device. So for example, assume that the green light travels into the depletion width of this p-n junction. resulting in the generation of electron-hole pair. Electron moves towards the n-type layer and hole moves towards the p-type layer. Consider the long wavelength. We know that long wavelength has small absorption coefficient, means higher absorption depth. So long wavelength travels deeper into the semiconductor device, resulting in the generation of electron-hole pair. Now this electron would travel towards the left and hole would travel towards the right. Now just like this hole, the electron in the p-type layer also has a certain lifetime, and it's going to travel, it can travel a particular distance within its lifetime called the diffusion length. So if this electron-hole pair is generated within its diffusion length, then it can travel towards, they can travel and get collected by the electrodes, and they can contribute towards power by the solar cell. So essentially the total width which results in contribution to the solar power is actually determined is actually the sum of this diffusion length for holes plus width of the depletion region plus diffusion length of the electrons. Here is a diagram of the construction of the solar cell, where we have an n-type layer, we have a p-type layer. Another point that I need to mention in this structure is that the n-type layer where the light enters need to be thin, so that the light can enter through the thin layer and it can get to the depletion width, and it can also get to the p-type layer. So generally this layer is thin. In this configuration we see that the back layer, the p-type layer, is entirely covered with metal. Well, the top layer, we do have contact on the top layer, but it's not fully covered with metal. What is the reason for that? If we fully cover this entire layer with metal, we know that light can be reflected from the metal, so it's going to decrease the conversion efficiency of the solar cell. But we also need metal so that we can collect carriers, we can collect electrons at the top surface. So we have a bus electrode and then we have finger electrodes. The finger electrodes are extended so that carriers anywhere close to this region can be collected by the finger electrodes. But we also need to make sure that they have enough space so that we can have maximum absorption efficiency by this top layer. Solar cell characteristics. The important parameters of a solar cell are the photocurrent or short circuit current, the open circuit voltage, the series resistance. We know that a solar cell has a p-type layer and it has an n-type layer. And these semiconductors have a particular resistance according to the formula R is equal to rho L divided by A, and then rho is the resistivity is equal to 1 over Q times mobility times the carrier concentration. So the p-type layer has a certain resistance and the n-type layer has a certain resistance, and both of them add up resulting in a series resistance. And also another important parameter that we care about is quantum efficiency. Also another parameter is fill factor. So these are the parameters that we really care about in solar cells. We already discussed this phenomena in which we already mentioned that shorter wavelength light has large absorption coefficient and it can travel shallower into the semiconductor device. Medium wavelength light has medium absorption coefficient and it can travel up to a medium distance inside the semiconductor device. Similarly, long wavelength light has a smaller absorption coefficient and it can travel deeper into the semiconductor device. As we already discussed that the fundamental or the basic building block of a solar cell is a p-n junction. So let us revisit some of the concepts of a p-n junction. In a p-n junction, we have a p-type layer. The p-type layer is on the left. We know this because the Fermi level is close to the valence band. And we have an n-type layer, and the n-type layer is on the right. We know this because the Fermi level on the right is close to the conduction band. So initially there is diffusion of electrons from the n-type layer to the p-type layer, and diffusion of holes from the p-type layer to the n-type layer, and after a certain point the system it arrives at equilibrium. Then we have a constant Fermi level, and then we see that there is a barrier for electrons to move from the n-type layer to the p-type layer, and we have a barrier for holes as well to move from the p-type layer towards the n-type layer. This barrier is called the built-in potential barrier, essentially blocking carriers to move across the junction at this point. But what happens under forward bias? Under forward bias, we apply positive potential to the p-type layer and negative potential to the n-type layer. And we also know that whenever we apply positive potential to any side of this energy band diagram, that side of the energy band diagram is dragged down. So all the energy levels on the p side would be dragged down. So now we see that the Fermi level on the p side is lower as compared to the Fermi level on the n side, resulting in a decrease of this barrier. So now carriers can easily flow from the n-type layer to the p-type layer, and similarly holes can easily flow from the p-type layer to the n-type layer. So this was under forward bias. Now what happens under reverse bias? In reverse bias, we apply positive potential to the n-type layer and negative potential to the p-type layer. When we apply positive potential to the n-type layer, it means we drag down all the energy levels on the p side, resulting in an increase of this barrier on both sides for the holes and also for the electrons. So essentially this current due to diffusion is zero. But also we know that there are some minority carrier holes in the n-type layer and minority carrier electrons in the p-type layer. And we apply positive potential to the n-type layer, so this positive potential attracts this electron, and this electron flows to the n-type layer due to the electric field. So and also this hole flows towards the p-type layer due to the electric field, because we have negative voltage at the p-type layer. So it's going to attract this hole from the n-type layer. Which means that even under reverse bias, a small current would flow due to minority carriers, due to drift, resulting in a small reverse current. But how do we relate it to the solar cell? So now let us understand the concept of a solar cell. What happens in a solar cell? In a solar cell, we have a p-n junction. Light is incident on this p-n junction, resulting in the generation of carriers in the p-type layer, in the n-type layer, and also in the depletion region. So then electrons move towards the right and holes move towards the left. And in this process, when electrons move towards the right and holes move towards the left, and these additional electrons and additional holes, they are generated by the incident light. When the incident light has energy which is greater than the band gap of the semiconductor. So when these electrons move towards the right and holes move towards the left, so now we have separation of charges, right? And this separation of charges then essentially results in an applied voltage across this energy band diagram. Negative charges on the right, positive charges on the left, so it's kind of forward bias. This voltage is accommodated across the depletion region. So this is going to reduce this barrier. When it reduces barriers, now we also give a chance to the electrons to flow across the barrier because of diffusion. So in case of a solar cell, we have two kinds of currents. We have the diode current as a result of diffusion flowing from right towards the left, and we have drift current as a result of the photocurrent, or we also call it the short circuit current. So here is the IV characteristic of a diode under dark conditions, under no light. We know that there is a small reverse leakage current, and the forward current is exponentially proportional to the applied voltage. And because of the incident light, there is flow of carriers resulting in a photocurrent. So here let us consider these configurations. Consider this solar cell short circuited. So we have short circuit current flowing across this configuration because of the incident photons. And under open circuit condition, no current flows, the voltage would be maximum. We call it the open circuit voltage. If we connect an external resistor across this configuration, so now once again we have two currents. We have the diode current flowing in one direction because of diffusion, and we have the photocurrent flowing in other direction represented by the green loop. The photocurrent flows because of drift, because of the incoming photons. The net current is the difference between the diode current and the photocurrent. Consider the same solar cell under different conditions. So consider this rectangular block as a solar cell. Under open circuit, we will observe a maximum voltage. We call it the open circuit voltage. However, the current would be zero. And we know that power is the product of voltage and current. So the power delivered by this configuration is zero. Consider the short circuit situation. Under short circuit, the voltage would be zero and the current would be equal to short circuit current. Now in this configuration, once again we know that power is the product of voltage and current. So the power delivered by this configuration is also zero. Consider a third situation when we connect a load to the solar cell. It results in a particular voltage, in a particular current. The power delivered by this configuration is equal to the voltage times the current. We already discussed that we have two kinds of currents flowing in a solar cell. We have the photocurrent as a result of the incident light, and this photocurrent is directly proportional to the light intensity. The light intensity is given in watt per meter square, and K is a constant. It is a device dependent constant. Similarly, we have diode current, and we already know the formula for diode current. Diode current is equal to the reverse saturation current times exponential of E times the applied voltage divided by KT minus 1. We also have N, where N is the ideality factor for non-ideal diodes. For ideal diodes, N is equal to 1, but for non-ideal diodes, N can have a value above 1. These non-idealities come from different scenarios. For example, the incident light results in the generation of electron-hole pairs, but these electron-hole pairs might recombine because of Shockley red hole recombination, because of defects inside the band gap of the semiconductor, defect levels, or because of Auger recombination, or because of other non-radiative recombination phenomena. So for the solar cell characteristics, our total current is the difference between the diode current and the photocurrent, where I naught here is the reverse saturation current. We already discussed it. And N is the ideality factor. For a silicon solar cell, the ideality factor is 1.5, and the reverse saturation current is roughly in micro in this range, nanoamps range. Let us talk about the solar cell IV characteristics. Under dark conditions, under no light, we have this IV characteristic. What happens under light? Under light, this current increases because we also have the photocurrent now. So at under short circuit condition, this point would give us the short circuit current, the maximum current that flows through the configuration under short circuit. And we start increasing the resistance connected to the solar cell, then the current would start decreasing, but the voltage would start increasing. And when under open circuit, when the resistance is infinite, the current would now be zero, and this gives us a maximum voltage. We call it the open circuit voltage. Now what happens if we double the intensity of light? So we know that the photocurrent is directly proportional to the intensity of light. If we double the intensity of light, the short circuit current would also be doubled, or the photocurrent would also be doubled. There is a slight increase in the open circuit voltage as well. However, it's not directly proportional to the open circuit voltage. And we have an example based on that, so we can understand it better with the help of that example. Now, here is a plot for short circuit for current versus voltage of a photovoltaic module. Here, like you can see, the open circuit voltage is around 20. So we are not talking about a single solar cell. A single silicon based solar cell would give us open circuit voltage around 0.5, 0.6, 0.7 volts. But if we connect multiple solar cells, like 20 of them in series, like 40 of them in series, it's going to give us an open circuit voltage of around 20 volts. So we are talking about a photovoltaic module. And we have light intensities. So when we keep increasing the light intensities, we see that our photocurrent is also increasing accordingly. And the open circuit voltage is also increasing, but the increase is slight. It's not a major increase. So the takeaway point is that the photocurrent is directly proportional to the light intensity according to this formula, IPH is equal to KIL. But the open circuit voltage is not directly proportional. There would still be increase, but the increase is small. And we will understand it with the help of an example later. Here is the solar cell IV characteristic. So as already discussed, that under short circuit condition, we will observe a maximum current. And then when we keep increasing the resistance, the current would start decreasing and the voltage would start increasing. Under open circuit, we will have open circuit voltage, maximum voltage achieved from this solar cell configuration. And assume a load resistance of approximately, for example, load resistance of 30 ohms. So for this configuration, when we connect this resistance to the solar cell, how do we determine the corresponding voltage and current point for this resistance? So in order to determine that, the slope is actually determined by 1 over the resistance. So find the slope and then draw a line from the origin to this curve. And this line actually crosses this curve at this point. So then find the corresponding current and the corresponding voltage for that point. So in the next slide, we have an example. Consider a solar cell driving a 30 ohm resistive load. The cell has an area of 1 centimeter by 1 centimeter and is illuminated with light intensity of 600 watt per meter square. A V curve is shown in slide number 39. What are the current and voltage in these circuits? So we already discussed that we need to determine the slope and then draw a line onto the curve. This point gives us the corresponding current and the corresponding voltage for this resistance across the solar cell configuration. So the corresponding current is 14.2 milliamps and the corresponding voltage is 0.425 volts. The second point is, what is the power delivered to the load? The electrical power delivered to the load would be the product of current and voltage. We already know the current and voltage, so this comes out to be 6.035 milliwatt. What is the efficiency of the solar cell? We know that efficiency is equal to output divided by input into 100%. Now, what is the output power? The output power is the electrical power, this power, right? What is the input power? The input power is the optical power, which is the product of light intensity into surface area. So convert this surface area into meters square and multiply it with light intensity. It gives us the input optical power. So efficiency is equal to output electrical power divided by input optical power into 100. It comes out to be 10.06%. Not a great efficiency. Current collection topic. There is another parameter, it's called the fill factor. So ideally from our solar cell we would like to achieve the maximum power, and the maximum power would be the product of VOC and ISC, but we know that under open circuit condition the current is zero, so the power is zero at this point, and under short circuit conditions the voltage is zero, and power is the product of voltage and current, so the power is once again zero at this point as well. But once we start increasing the resistance across this configuration, we see that the current starts decreasing and the voltage starts increasing, and we get to a point which gives us the maximum power on this curve. The current corresponding to that maximum power is called the maximum current, and the voltage corresponding to that point is called the maximum voltage. So basically we get two rectangles. This red rectangle from the product of ISC and VOC, ideal power, and the blue rectangle from the product of maximum current and maximum voltage. And the ratio of the two rectangles is called the fill factor. So it's kind of like a container. You would like to fully utilize the container by filling it up, but that under non-ideal conditions that is not the option. So we would like to fill it up as much as possible. So you would like to have as high fill factor as possible. So fill factor is the ratio of VMIM divided by VOC ISC. And P maximum, which is V maximum into I maximum, is the product of fill factor into VOC times ISC. And from this formula for the efficiency, we know that efficiency is equal to output power divided by input power. Output power is VMIM. VMIM is equal to fill factor into VOC ISC. So efficiency is equal to fill factor into VOC ISC divided by the input optical power. So here is a simple relationship in order to calculate the efficiency of a solar cell. Now, and here is the power curve. So here is the IV characteristics where we have VOC, ISC, and the maximum power point. Power is the product of the current and voltage. So the power starts increasing, it gets to a maximum, and then it starts decreasing once again. So it gives us a maximum power at a particular load resistance. Why is the fill factor not ideal? Why is it not as high as possible? Because of a couple of reasons. First, We have series resistance of the N and P type layers, as we already discussed. So, talking about the series resistance, as I told you that the N and P type layer, the P type layer and the N type layer have their own resistances. R is equal to rho L divided by A. So the fill factor is smaller, first because of the series resistance, and secondly, when these carriers travel across the p-n junction so that they can be collected by the electrodes, sometimes what happens is they start traveling across the surface of the device, because we might have defects on the surface, we might have dangling bonds on the surface, and that actually contributes to the parallel resistance or the shunt resistance of the device. We would like to have as small resistance or S series resistance as possible, and we would like to have as high shunt resistance as possible. Here is the solar cell equivalent circuit. We know that in a solar cell we have photocurrent flowing in one direction, and then we have diode current flowing in other direction, and then we have the parallel or the shunt resistance and the series resistance. The voltage that appears across this configuration is the diode voltage minus I times Rs. And this current, net current, is the difference between the diode current and the photocurrent. What is the effect of the series resistance? So as I told you that ideally we would like to have zero series resistance, resulting in this blue curve which has a decent fill factor. If the series resistance is increased to 20 ohm, then we get to this curve. Now it has a smaller fill factor, resulting in a lower efficiency of the solar cell. If we further increase it to 50 ohms, then we further reduce the fill factor of the solar cell, further resulting in a further decrease in the efficiency of the solar cell. What happens if we have two solar cells connected in parallel? Here is a parallel configuration of two solar cells. In parallel configuration, their current is doubled, however the voltage remains the same. So here is an example of the parallel configuration. So assume that like one cell gives us 10 milliamps of current, then two solar cells would give us double current, 20 milliamps. However, their open circuit voltage would remain the same. And when current is doubled, the power is also doubled. There could be different kind of losses in solar cells. If the photon energy of the incoming light is smaller than the bandgap of the semiconductor, it will not result in generation of electron-hole pairs. So this is one reason for reduced efficiency of the solar cell. Secondly, if the photons have excessive energy, which means shorter wavelength photons, as I already discussed, they are going to be the electron-hole pairs will be generated close to the surface, and then they would be recombined, not contributing to the solar power. Similarly, collection efficiency of the solar cells, if we have too large a distance between the created electron-hole pairs and between the contacts, these generated carriers might be recombined at some point. And then because of fill factor, because of series and shunt resistances. So there are so many different reasons for losses in solar cells. Loss mechanisms in solar cells could be optical or could be electrical. One of the reasons of losses is reflection. For example, light can incident on this surface but might be reflected back. The second is incomplete absorption. If the energy of the incoming light is smaller than the band gap of semiconductor, it's going to travel through the semiconductor, but it might be reflected back and out into the outer atmosphere. Another reason could be shading. We have electrical contacts, and light is going to be reflected from these electrical contacts. Electrical losses contribution comes from parasitic resistance, from the series and shunt resistance, and also from recombination, recombination of carriers. Recombination could be Shockley-Reed-Hall, OJ recombination, or radiative recombination if the carriers have to travel a long distance to the N and P type layers into the electrodes. We already discussed non-idealities in solar cells. One of the solutions to improve the efficiency of solar cells is to apply anti-reflection coatings to the solar cells. It can improve the efficiency by up to 4%. So anti-reflection coatings actually match the refractive index with the refractive index of the semiconductors, resulting in improvement of the efficiency. We can also improve the performance or enhance the performance of the solar cells by creating inverted pyramids, textured surface morphology onto the solar cells. So for planar surface, there is a high chance of reflection. If we have inverted pyramids, even if this light gets reflected, it's going to be reflected back into the semiconductor, resulting in enhanced performance of the solar cell. Another approach to improving the efficiency of solar cells is band gap engineered solar cells. So for example, we might have at the top we might have a wide band gap material, and then we might have layers of narrow band gap materials. Gallium arsenide has a band gap of 1.4. Aluminum gallium arsenide, depending on the aluminum and gallium content, is going to have band gaps higher than 1.4, around roughly you can say 2 electron volts. So the high energy photons would be absorbed by the top layers, and the low energy photons would be absorbed by the bottom layers. Same concept once again. Another approach is tandem solar cells, in which we connect 2 or in fact 3 solar cells via tunnel junctions. Without tunnel junctions, the carriers would be trapped inside the individual solar cells. But via tunnel junctions, we connect them together so that electrons can travel towards the left and holes can travel towards the right and get collected by the corresponding electrodes. Here I've listed the solar cell efficiencies of a few kind of solar cells. For example, single crystalline silicon, according to this table, can give a maximum efficiency of 21%. In fact, recently in literature, we can achieve a maximum of around 26.5% for silicon-based solar cells. Consider an example. A solar cell with a light intensity of 500 watt per meter square has a short circuit current of 10 milliamps and open circuit voltage of 0.5. What are the short circuit current and open circuit voltage when the light intensity is double? So we already know that light intensity is directly proportional to the short circuit current is directly proportional to the light intensity. So if the light intensity is doubled, the photocurrent would increase from 10 milliamps to 20 milliamps. So this is simple and straightforward. But what happens to the open circuit voltage when the light intensity is doubled? It requires some more calculations. We know that the total current is the combination of the diode current and the photocurrent. And under open circuit conditions, the total current would be 0. So set these two to 0. Furthermore, here n is ideality factor. It is not efficiency. It's actually the ideality factor in this equation. We also know that VOC generally is much higher than E charge on electron divided by NKBT. Like this has a value of 0.0259 and VOC at room temperature, and VOC is in this example is 0.5, so this is much greater. So this exponential would result in a number much greater than 1. So we can ignore this 1 as well. Then rearranging this equation, we get to this form. The goal is to calculate the open circuit voltage. Now we have two situations. In one situation, the short circuit current is 10 milliamps and the open circuit voltage is 0.5. We nominate it as VOC1 and IPH1. And in the second situation, the ISC is doubled to 20 milliamps, but we don't know VOC. So in the second situation, you can assume it as VOC2 and IPH2. And then subtract the two from each other, reorganize the equation, we get to this form. And then move VOC1 to the right side of this equation. So VOC2 is equal to VOC1 plus this factor, natural log of I2 divided by I1. Intensity 2 divided by intensity 1. 0.5 plus, after some calculations, VOC2 comes out to be 0.52 volts. So when the light intensity is doubled, the current increases from 10 milliamps to 20 milliamps, the photocurrent. And the VOC, the open circuit voltage, increases from 0.5 to 0.52. So the takeaway point is that there is 100% increase in the photocurrent. However, there is only a 4% increase in the open circuit voltage. So increase in light intensity impacts the photocurrent a lot, but it has a minor impact on the open circuit voltage. Then here is your homework. 6.1, 6.2, 6.3 given in the slides, and the physical constants are also given. Please submit the homework by the next lecture. That concludes